Hi and hello once again. So we are on our next problem, which is problem number 7, and this problem is under the lesson 6, transmission and distribution, and we are on performance of the line. Okay, so before we proceed with the problem here, if you want to have a copy of our problems with the supplementary problems as well, you can go to the description link, or description tab rather. And then from the description tab, you can see the link on this video. And then from there, you can have the problems and supplementary problems as well. So from there, you can solve the problems and then you can have a mastery of the subject matter. Okay? And then you can learn. Okay, now from that, we can now read the problem here on number 7, which is an interesting problem, a problem in terms of medium lines, which is the end condenser method. Okay, let us read the problem. A medium single phase transmission line. So please take note before we go to the problem solving here. It is a single phase 2-wire line. Okay, take note of that. And it has the following constants. First, you have the resistance per kilometer of 0.25, reactance per kilometer of 0.8, the susceptance per kilometer 14 times 10 negative 6 mhos, and the receiving voltage is 86 kilovolt. We assume that this problem is already in an end condenser mode, no, which is the capacitance is concentrated at the receiving end of the line. So for this, if the line supplies 15,000 kilowatt 0.8 power factor, we need to determine the voltage at the sending end, the current at the sending end, the voltage regulation, as well as the supply power factor. Okay, so in this case, it's already expected. The problem is an end condenser. So we have the following given as well: the resistance per kilometer, the reactance per kilometer. The length of the line, by the way, is 100 kilometers, which is we can now treat the system in terms of medium line. Okay, because medium lines is 80 to 140 kilometer with that range. And from here, we have the susceptance. Okay, the susceptance here can be regarded as your admittance already, simply because from our okay, sorry for that. From our fundamentals, we can regarded your conductance as 0, simply because we can have the resistance, shunt resistance, as negligible as possible. And then we have this relationship. But again, no, your susceptance here is the reciprocal of your capacitive susceptance, or yung capacitive reactance, other capacitive reactance, which is your XC. So for this, we can now have the equation in terms of J omega C, right? So this basic fundamentals here are already discussed from your parameters of the line, from the performance of your line in terms of the medium type, which is the end condenser. All of those with the corresponding phasor diagram is already discussed. Okay, now the PR is receiving power is 15,000 kilowatt of 15 megawatt. Power factor receiving is 0.8. Now we can now draw the per phase or the per phase analysis of the system. But again, it is not already in per phase, simply because we have a single phase 2-wire. So definitely, whatever your receiving voltage here is also your per phase voltage. Okay, so you have here your VS, your ZL, your C, and your receiving end voltage. Please take note that the VCN here is equal to VRN in terms of vector. And one more thing, by KCL, your IS simply equal to IC plus IR. So again, we are reviewing the by using circuit theory, the circuit or the wiring diagram or the per phase diagram of your N condenser method. And this N condenser method, by the way, is like your power factor correction circuit, simply because the capacitance is already localized at the receiving end. Okay, now, in terms of solution, we need to get first some preliminaries. We need to multiply the 0.25 by the length. The answer is 25 ohms rather. Multiply 0.8 by 100, you have 80 ohms. Multiply 14 times 10 negative 6 by 100, you have 14 times 10 negative 4 mhos. And please take note, if you want to get the phasor, don't forget the J here. Okay, sometimes I call it the damn J. Damn J, simply because this 1 bar positive 90, if you forgot this one on the calculation, you can get the results are wrong. Okay, simply because in the first step you forgot to have the J parameter, so that it will become a phasor. Now you get IR in terms of magnitude, but as you can see here, there's no square root of 3, simply because we are in a single phase 2-wire system. And you have PR over VR PFR. Please take note, if this is apparent power SR, you do not need to have the power factor at the receiving end. If that is SR, definitely that is SR over VR only. But since this is PR, or the power at the receiving end, you need to divide it by the power factor at the receiving end. Okay, in this case, 15,000 times 10 to the 3, all over 66K times 0.8. The answer is 284.09, and please take note, to have a phasor, okay, don't forget the inverse of the cosine of your 0.8, so that you can now get the theta, because the power factor is cosine of the angle theta, and then theta is the inverse, of the power factor. Okay, so that is cosine negative 1 of the power factor. Okay, in this case, the answer is 36.87, and based from our Cisco table, this is negative, right, for a lagging condition. Since this is theta r, the reference definitely is your VR, bar 0. So that's why we can still use the Cisco table, wherein the I is lagging condition, wherein that is negative 36.87. As we have discussed here, we can now get your Y here, that is J omega C. So this is your Y to get the charging current IC. We already described this one on the basic fundamentals, and you have here your Y as 14 times the negative 4, then your VR 66K times J. And hence you have your IC here. Don't forget, it has a phasor. It has your J here, bar 90. Don't forget that. And your IR here has a phasor. It must have the theta R, which is 36.87. Okay, now we can now proceed to the solution, again, the continuation of the solution on our next slide. Stay tuned. Hi, and hello once again. So we are on our conclusion of problem number 7. As you can see here, I rewrite the wiring diagram, or the per phase basis of the N condenser here, so that we can recall the parameters here, and we can use circuit theory in order to get the requirement of the problem. Okay, so we already established from the preliminaries the values of IR, IC, by the way, IC, and then we can now get IS by using KCL. So you have here IS. Now from letter A, you have IS, IC plus IR. So we have the following values: 284.09 bar negative 36.87 for IR. IC is J 92.4. If we add this up, we have 240.30 bar negative 18.95. Please take note, this is your theta IS, or the sending in bar angle of the current. So this is your theta IS.
Now, you need to get theta Vs, which is your alpha, your transmission angle. And how can you get this one? Simply by using a little bit, no, of your circuitry. If this is VCN is equal to VRN here, which is our reference, as we have mentioned, no, from our basic fundamentals, therefore this VRN bar 0 plus the drop IS and R plus JXL is simply equal to VSN. And that's why we established this one. We do not need to memorize, no, formulas, simply because the formulas can be easily derived. You have a circuit and then a little bit of circuitry. Then from that analysis, you can now have your own formula. And this is definitely looks from the short line. The only difference is instead of IR, IS. But please take note, the IS is not equal anymore to IR. Okay? It's not equal anymore. Your IS not equal to IR because of the condenser. Okay? You need to add the condenser current plus IR to get IS. Okay, for that, all of the parameters is already here. But there's no square root of 3 no, on the 66K simply because our given is single phase to our system. And then from here, straightforward, you have 66K to 40.3 bar negative 80.95, the result of IS, and then 25 plus J80, the R and XL respectively from our preliminary computations. And thus, the answer no, for your VS, and it is also equal to your VSN simply because single phase, 79.597 no, kilovolt in terms of magnitude, but we need to have the angle as well, the transmission angle, which is your theta Vs as positive 11.766. Okay, it's very, very important that you know the polarities, simply because the polarities it will have a useful, okay, we can use that rather no, on the power factor in determining the condition of the power factor. It's very useful. Okay, now in this case, you can now get C, the voltage regulation. We have Vs minus VR over VR times 100 from your electrical machines. And thus, we can now get no, the VR here, 79.59 minus 66 over 66, the K will cancel out, cancel and cancel, definitely, and we have 20.6%. Now, in order to get the supply power factor, I already have a ready-made equation here, but the question is how it is arrived or derived. So please take note, we will use the EBD, the electric body diagram, in order to do this. In physics, you have free body diagram. In electrical engineering terms, in transmission line, we have the EBD. EBD means electric body diagram. And this is our referencing. So all you have to do is to get the angle of your voltage and current, and then from there, we can now get the condition of the power factor and the power factor angle as well. Now, in this case, you have positive. So positive, you turn the angle in counterclockwise direction. So please take note, this is like your phase sequence. So this is your theta Vs, which is equal to alpha. Okay. And then you have a negative 18.95. So I assume like this. This is your theta Is. And then from here, this is your theta S. Okay. Which is definitely equal to this. You need to add the angles of your Vs and your current. Now, in order to get, okay, the condition of the power factor, you can recall this one. The power factor is lag. If your I will lags the V by a certain angle, theta. Otherwise, it is a leading power factor, right? Now, it's pretty clear. If your Vs or your V or the right of the statement is reference, this your right of the statement is reference, so RIR, and the left of the statement is the rotating phasor. Okay? So from here, you have your reference here. You turn the angle theta S in a clockwise manner. And a clockwise manner means it is a lagging condition. And thus, whatever, no, the cosine of this, no, with your theta s, it will become a lagging condition because the angle theta s is in clockwise direction in terms of I will lags the voltage by certain angle, which is in this case is theta s. Chipips, kapatid. Chipips. So if you already know the phase sequence, and again, no, this is just a refresher and recall from our last lectures, you easily understand, know, how to get, the angle condition. And this is 110% sure in terms of phasor diagrams. Okay, so our problems become interesting. We can now go forward to problem number 8.